Welcome to the last week of videos. Humke's office, at least for a while. In this video, I'd like to talk about a couple of important topics here, or things to compute in 3 dimensions. But to begin, let's talk about 2 dimensions, and I'll look at some analogs in 3 dimensions. Let's be given a vector field F. So here, f of x and y will be equal to PQ. Each one of these is a function of x and y. And over here, f of x and y and z will be a function, will be this triple, PQR. Each one of these is a real valued function of x, y, z. And I suppress the x, y, z's here just because it takes up a lot of space. Here we were interested primarily in curves, and we had the parameterization. Over here we're going to be interested in what we did with line integrals will also work here, but primarily here, or in addition, we're going to be interested in surfaces. S, and we'll have a parameterization there too. We've dealt with surfaces before. A curve will have a parametric form. U of t will be x of t, y of t, t in some domain. Over here, the parameterization will be u of s and t will be x of s and t, y of s and t, z of s and t, and s and t will be in some domain. I'll make this domain simple, but it doesn't have to be 0 to 1. And here, 0 less than or equal to s and t less than or equal to 1. So we're looking at these analogs. Now also let temp be a real valued function from the plane into the reals, and let temp be a real valued function from free space into the reals, continuing this analogy. So one of the things we might want to find is the average temperature on the curve, or over here, the average temperature on the surface. So we want to be able to integrate temperature. I'm going to erase some things, but remember this setup here. I'll use this notation. So for example, for moments or average temp, other integrals of real valued functions, we'd like to integrate over C the temp function. This is equal to the integral from 0 to 1 temp of alpha of t times alpha prime of t dt. And the absolute values go here, meaning that this is the expansion contraction factor. In this case, it's the speed. And over here with these surfaces that we've integrated, and we've found these averages already. So this should be a review. This is a double integral of the temp of u of s and t times the expansion contraction factor u prime of s and t ds dt. So these integrals we've already done. We'd like to integrate vector fields now on both of these. So that's a different ball game here, because a vector field is a vector valued function. Vector field here is a vector valued function defined on 3 space. And we'd like to be able to integrate these. In R2, there are 2 integrals that we have done on curves. Along the curve. So this is the integral on the curve of f dot t, and across c, which is the integral over c of f dot n. And so these 2 concepts we've looked at. We have Green's theorem in 2 varieties. We want to look at analogs. What works in 3 space? Can you do this same stuff in 3 space? Let's take a look. So let C be a curve. We can certainly do the integral of f. We can certainly do this in 3 space. It works exactly the same. Parameterize the curve with alpha. And so this would be 0 to 1 f of alpha of t dot alpha prime of t dt. This is a dot product here. And this gives the work done by the force along C. This is the integral of the force along C. But this one has some problems. The main problem here is that if you have a curve, there is no specific normal vector to that curve in 3-dimensional space. The tangent vector, unit tangent vector, makes a lot of sense. And we could integrate with respect to the direction that we're turning in, which is our n vector. We have an n and a b that we've computed. And we could do this normal vector just the way we did this one. That also works well. But if we just want to take the normal to the tangent, there isn't a normal tangent vector here. There actually is a normal tangent plane here. So at every point, there's a little tangent plane that is perpendicular to the curve. So in a way, unless we use the n that we already have, this is not well defined because there are plenty of normal vectors. But if we replace C by a surface, then this is well defined. If we take a surface here in 3 space, and we have a vector field at every point, in particular every point of the surface, we can, this surface at every point does have a well-defined normal vector. So we could project this onto the normal vector and integrate that on the surface. And in fact, that is what is called a surface integral of a vector field. Taking our vector field F, projecting it onto the normal to the surface to get this length here, that would be F dot n, and then integrating over the surface. So this is what we'd like to do. We already know how to integrate functions that are real valued. So it's just a matter of finding a formula for what this is and then deciding how to integrate over that surface. So that's what I'd like to talk about right now, is integrating that vector field F over that surface. So we have this surface defined by two variables. So this will be an x of t, y of t, z of t. We've already found tangent planes to the surface, and to find the tangent planes at any given point, we needed two directions, a dir1 and a dir2. And the dir1 was, these should be S and T. Since U is a function of S and T, each one of these are functions of S and T. And so one direction is the derivative of x with respect to S, derivative of y with respect to S, derivative of z with respect to S. This is a vector that is in the direction of this surface at any given point. And dir2, which is the same with respect to t. So these are two directions here. If we take the cross product of these, we'll get a normal vector. So dir1 cross dir2 is a normal vector to the plane. And then we want to normalize it, divide by its length, multiply by the expansion contraction factor, and integrate. So let's just take a look at that. So this is ijk when we're taking the cross product, x sub s, y sub s, z sub s, x sub t, y sub t, z sub t. This vector will be perpendicular to the plane at any given point, but this vector will not be a unit vector. We'll have to make it a unit vector. So I gets multiplied by ys zt minus zs yt and so on, minus xs zt minus xt zs. And then finally, the last one is xsyt minus xtys. So this is a perpendicular vector to the surface at any given point. And now we have to multiply by or divide this by its length. So this will be the integral. S will go 0 to 1, t will go 0 to 1. This will be f of u of s and t, f of the parameterization that we have, dot, and this thing, dir1 cross dir2, which we've just computed, divided by the length of dir1 cross dir2 times the expansion contraction factor, ds dt. So here is the integral of the normal component of the surface, integrated over the surface. And although I won't do the details right now, it's easy to see that this expansion contraction factor is exactly the same as the length of dir1, dir2. Maybe I'll just do that. here is u of s and t. And so we want to compute its derivative. So this will be a matrix. We have an x, a y, and a z, and an s and a t. So this is x sub s, x sub t, y sub s, y sub t, z sub s, z sub t. So the expansion contraction factor consists of the square root of the sum of the squares of the determinants of the square matrices in here, the maximum ones. Here's the first one, xs yt minus xt ys, the quantity squared. And that's this component squared. When you take the length of this down here, you're going to have that same term. The next one would be yszt minus ytzs squared. And that's this one here. And then we've got one more under the square root, and that will be this one. This is a negative, but just exactly like we did with the curves. When you square it, that goes away. So these two are exactly the same. So the surface integral, f dot n over the surface, is equal to vector field evaluated on the surface. This will be a 3D vector. dir1 is the derivative of this u with respect to s. dir2 is the derivative of u with respect to t. The cross product is a three-dimensional vector. It happens to be normal to the surface. This dot product integrated 0 to 1 ds dt will give this surface integral. And we're going to be looking at this surface integral. This surface integral is, notice that this is the integral across the surface because we're integrating the force in the n direction. All right. Now there are a couple of quantities that are important in the calculations that we do. In R2, a couple of quantities that we did that came up were this: the partial derivative of q with respect to x minus the partial derivative of p with respect to y. I called this f perp. And this was perpendicular. In a way, this was useful when we were doing Green's theorem. This came about. And the other one that came about in the form that I gave you is the trace of f prime. So both of these were important, and this was p sub x plus q sub y. The trace meaning the sum of the terms on the main diagonal. In R3, there are two analogous quantities that come up. Now in R3, f is p, q, and r. So this vector was perpendicular to PQ. So we want a vector that is perpendicular in a way to PQR to be the analog of this. And this is called the curl of F. And it's computed, not surprisingly, with a cross product type matrix. Partial with respect to X, partial with respect to Y, partial with respect to Z, P, Q, R. So this is the definition of curl. It plays the role of this guy here. And in a way, there isn't a nice little format. It's similar, but in general, this cross product notation is used in higher dimensions. And the analog here is not just an analog, it's identical. It's the trace of F prime. F prime, F has PQR, so F prime in this case is a matrix. It was the last time too, but it's P sub X, P sub Y, P sub Z, these partial derivatives, Q sub X, Q sub Y, Q sub Z, R sub X, R sub Y, R sub Z. And the trace is the sum of the diagonal elements, just like it was over here. Sum of the diagonal elements is called a trace. And these are the two quantities that are the analogs of these in discussing what happens to Green's theorem in 3 dimensions. So Green's theorem in a way divides in 3 dimensions. We'll be looking at the analog of integrating a force field along a surface or along a curve and across a curve. Across a curve, the analog will be across a surface. And Green's theorem has a little different analog with regard to the other one. So we'll talk about those. That will finish the course, these 2 theorems, and we'll talk about both of them next time. So I'll give you a few problems with these. I'd like you to be able to compute these. These are easy to compute. I want you to think about them as analogs to these 2 in 2 dimensions. Our book does not do it this way. I gave you kind of the mathematical approach to this. And maybe we'll do a couple of surface integrals just to get the hang of doing a surface integral. Okay, see you Monday, and have a good rest of the weekend. Sure is nice out there right now.